You've heard of this number. It's supposed to be in the Parthenon, in the Mona Lisa, in seashells, in sunflowers, in your own face. Most of that is exaggerated. But underneath the hype is a real number, with a real definition that genuinely does keep showing up in places you wouldn't expect. For reasons that have nothing to do with beauty and everything to do with a stubborn little rectangle. So forget the myths for a moment. Let's build the number from scratch and watch where it actually leads. Real quick, before the myths, there is no solid proof the Parthenon's architects measured it in on purpose, and the Mona Lisa claims are mostly modern pattern matching after the fact. What is solid is the math underneath. This is symmetry. Let's find out why. It starts with a rectangle that refuses to change shape. Take a rectangle and cut off the biggest square you can fit inside it, flush against one side. What's left over is a smaller rectangle. For almost every starting rectangle, that leftover piece is just some random shape, a different proportion than what you started with. But there is exactly one proportion where something strange happens. Cut off the square, and the leftover rectangle is the exact same shape as the one you started with. Not similar in a loose sense, identical proportions, just smaller. Shrink it, rotate it, and it lines up perfectly with the original. Finding that biggest square is simple. Its side length equals the shorter side of the rectangle. Slide it flush against one edge, and whatever sliver remains on the other side is your leftover rectangle, narrower but otherwise untouched. Try this with an ordinary rectangle, say one twice as wide as it is tall, and check for yourself. Cut the square away and the leftover strip is long and thin. Nothing like the original. Try a square-ish rectangle instead, and the leftover is short and stubby, also nothing like the original. Most proportions fail this test immediately, so this isn't a property every rectangle has. It's a single specific ratio of width to height that makes the self-repeating trick work, and only that one. Whatever that ratio is, it deserves a name. Call it phi. Take a 2-to-1 rectangle, cut away its square, and the leftover is a 1-to-1 square itself. Nothing like the 2-to-1 shape you started with. Take a rectangle close to a square, say 6-to-5, and the leftover after cutting is a long, thin sliver, 5-to-1. Every attempt drifts further from matching, except one. So let's actually solve for that ratio. Call the long side of the rectangle A and the short side B, so the ratio we want is a divided by B. Cut off a square with side B. The leftover rectangle has sides B and a minus B. For the leftover to be the same shape as the original, its long side to short side ratio must equal the same number. That gives one equation, A over B equals BA over a minus B. That's the entire self-similarity condition, translated from a picture into algebra. Everything else is just solving it. Sanity check the shapes. A and B are just lengths, so A is bigger than B, and a minus B has to be a positive, smaller length still. Otherwise, there is no square left to cut in the first place. That constraint is doing quiet work. It guarantees whatever ratio solves this equation is bigger than 1. Let phi stand for that ratio, A over B. Divide through and simplify, and the equation collapses into something remarkably clean. Phi squared equals phi plus 1. That's a quadratic equation, and the quadratic formula cracks it open immediately. Phi equals 1 plus the square root of 5 all over 2. Work out the decimal and you get approximately 1.618, going on forever without repeating. That number, born from nothing but a rectangle that wanted to repeat itself, is the golden ratio. The quadratic formula on phi squared minus phi minus 1 equals 0 gives two roots, 1 plus root 5 over 2 and 1 minus root 5 over 2. Only the first is bigger than 1, which our setup required, so that is the one that is actually a valid rectangle ratio, and the other root gets discarded. And that self-repeating trick doesn't have to stop at one cut. Since the leftover rectangle is a smaller golden rectangle, you can cut a square from it too. And the piece left after that is, again, a golden rectangle, smaller still. Keep going forever. Each cut leaves behind a perfect miniature of the one before it, spinning slightly as it shrinks, spiraling inward toward a single fixed point that the rectangles circle but never quite reach. You've built an infinite nested sequence of squares, each one sized by the exact same ratio as the last. Notice this process never actually finishes. There is always another square to cut, another leftover rectangle waiting. The spiral point at the center is a limit the rectangles endlessly approach but never land on, infinitely many cuts, packed into a finite picture. Now, inside each of those squares, draw a quarter circle, corner to corner, curving the same direction every time. String all of those quarter circles together, one per square, and they meet up smoothly into a single continuous curve. That curve is the golden spiral. It isn't decoration bolted onto the rectangles afterward. It's the literal, direct trace of the self-repeating cut. One arc per square, forever tightening around that same fixed point. Every arc curves the same rotational direction, the same way each cut rectangle rotated relative to the one before it. That consistent handedness is why the golden spiral, unlike a random squiggle, has a single well-defined direction of winding, and why it looks unmistakably like it is spiraling inward on purpose. There's a much faster way to sketch something close to it. Take the sequence where you start with 1 and 1, and every next number is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, 21. That's the Fibonacci sequence. Now build squares with those side lengths one by one, packing each new square flush against the previous ones. A 1 by 1 square, then another 1 by 1, then a 2 by 2, then a 3 by 3, then a 5 by 5. Each new square exactly fits the growing rectangle it's attached to. This sequence is named for Leonardo of Pisa, nicknamed Fibonacci, who introduced it to Europe in the year 1202 while explaining rabbit population growth. He almost certainly did not know it would end up tied to the same ratio the Greeks had already been drawing into pentagons more than 1,000 years earlier. Divide each Fibonacci number by the one before it. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 2 is 1.5. 5 divided by 3 is about 1.67. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. Watch the decimals. They're closing in, oscillating tighter and tighter around one number. 1.618. Phi again approached by a sequence that starts from nothing but the rule 1 plus 1. Notice the ratios do not creep up steadily, they oscillate. 2 over 1 overshoots phi, 3 over 2 undershoots it. 5 over 3 overshoots again, 8 over 5 undershoots again, each swing smaller than the last, squeezing phi from both sides at once like a vice slowly tightening. But be precise about what this is. The Fibonacci spiral, drawn from quarter circles in those square tiles, is a good approximation of the golden spiral, close enough that most eyes can't tell them apart. It is not identical. Only the true golden rectangle, built from phi itself rather than from whole number squares, produces the exact self-repeating curve. The Fibonacci version is nature's rough draft. The golden version is the finished mathematical object it's quietly aiming at. It matters because the Fibonacci version is built from whole numbers. You can actually count on a plant, 3 petals, 5 petals, 13 spirals one way, 21 the other. Real biology works in discrete counts. The exact golden spiral is the mathematical ideal that discrete countable growth can only ever approximate, never quite reach. Now for the place phi shows up exactly, no approximation needed. Draw a regular pentagon, all 5 sides and angles equal. Now draw one of its diagonals, connecting 2 corners that aren't next to each other. Measure that diagonal against a single side of the pentagon. The ratio between them is not close to phi. It is phi exactly, every single time, for every regular pentagon that has ever existed or ever will. This isn't a coincidence discovered by measuring. It falls directly out of the pentagon's interior angles, which force this exact proportion through nothing but plain trigonometry. Here is where that exact number comes from. A regular pentagon's interior angle is 108 degrees. Split the diagonal and 2 sides triangle it forms, and the resulting isosceles triangles have precisely the angles whose trigonometry forces the diagonal to side ratio to equal phi. No rounding, no approximation, straight out of the angle count. Now draw all 5 diagonals of that pentagon. Together they trace a 5-pointed star, a pentagram. Look at the small pentagon that forms in the exact center, where the diagonals cross each other. It's a perfect miniature regular pentagon, rotated slightly. Draw its diagonals, and another pentagram appears, with another tiny pentagon at its center. This repeats forever, each pentagon smaller by a factor of phi squared than the one before it. The same self-repeating idea from the rectangle, now hiding inside five-fold symmetry instead of four right angles. Measure the shrink factor precisely. Each nested pentagon is smaller than the last by exactly phi squared, not just some vague fraction. And this connects directly back to part 1, a rectangle that reproduces itself under one cut and a pentagon that reproduces itself under one star drawing are the same self-similar idea wearing two different geometric costumes. One last property explains why nature keeps landing on this exact number. Every irrational number can be written as a continued fraction, 1 plus 1 over some number plus 1 over another number, and so on forever. For most irrational numbers, those inner numbers jump around unpredictably. For phi, every single one of them is exactly 1. 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, forever, the simplest possible pattern an infinite fraction can have. That makes phi, in a very precise sense, the hardest number in existence to approximate well using simple fractions. Every other irrational number can be pinned down more efficiently. Phi resists more stubbornly than any of them. Compare that to pi, whose continued fraction runs 3, then 7, then 15, then 1, then 292, wild, unpredictable jumps. Or the square root of 2, which settles into a repeating 2, 2, 2 forever, but never the flat simplicity of phi's endless string of ones. That resistance to approximation is exactly what a growing plant needs. A sunflower adds new seeds one at a time near its center, each one turned by a fixed angle from the last. If that angle were a simple fraction of a full turn, new seeds would line up in straight rows, radiating outward, wasting the space between them. The angle that packs seeds most efficiently, leaving the least wasted gap no matter how many seeds grow, is the one-turn fraction that resists being approximated by simple fractions the longest. That angle is built directly from phi. Nature isn't chasing beauty, it's solving a packing problem, and phi happens to be the unbeatable answer. Run the numbers. A full circle is 360 degrees, and dividing it by phi squared lands you almost exactly on 137.5, the golden angle. Seeds planted turn after turn at that exact angle never realign into straight radial lines, no matter how many thousands of seeds a sunflower head eventually holds. So the golden ratio was never magic. It's the one proportion where cutting a square off a rectangle leaves a perfect miniature of itself, an idea that happens to also live exactly inside a pentagon's diagonals, and happens to be the hardest number to fake with a simple fraction, which is exactly why a sunflower would reach for it. If that gave you a small jolt of, oh, that's why, then that's exactly what symmetry is for. Subscribe, and every week we'll make one more piece of math or science click. And if it did click, a like helps this find the next curious person. Every one of those threads, the rectangle, the pentagon, the fraction, the sunflower, is the same fact about phi expressed in a different language.